You're challenged by a Young Earth Creationist. You're on the spot. They say, Bishop Ussher has traced the genealogies in the Bible back 6,000 years ago. God created the earth on a Thursday afternoon, despite a total lack of evidence. So, I'm going to give you some tools to debunk this stuff.
The Rational View is a weekly series hosted by me, Dr. Alan Scott, providing a rational, evidence-based perspective addressing important societal issues.
Hello and welcome to another episode of The Rational View. I'm your host, Dr. Al Scott. Thank you for joining me. On this episode, I want to delve a little bit into the science behind the age of the universe. How old is the universe? From the dawn of our species, the first sapient humans must have wondered how we got here. What put us on this earth? What was our history? And from that, many cosmologies emerged. And we talked about this with Dr. Janet Tulloch in the Big Bang Origin Story podcast. But we're in a very special place in history where we actually know the true answer, the physical answer as to how we got here, what the history is. For the first time in the history of our species, we know roughly how old the universe is. And you can look at my Observational Cosmology podcast if you want to get to the details. But in this podcast, I want to just go over a few independent lines of evidence that give you the story and how scientists know how old the universe is. Because just saying it's an age, it doesn't convince anybody. It doesn't. And if all you can do is say that, it's my point of view against your point of view, right? It's tribalism. So I want to give you some tools you can use if you're confronted by someone who's not aware of the evidence. Maybe someone who's been duped by one of those Young Earth Creationist organizations out there like the Institute for Creation Research or Answers in Genesis. And they've got pamphlets out there, glossy pamphlets out there that poke holes in evolution, poke holes in the basic science. It's basically a gish gallop against science, trying to sow doubt in the minds of their followers. Now, it should be noted that these organizations aren't really scientific. They don't have their own hypotheses. They don't test their own hypotheses. All they're doing is trying to poke holes in the consensus scientific explanation of how we got here. And they're really theistic anti-evolutionists, one might say. As always, if you enjoy my podcast, please send me a like, send me a comment. I'd love to hear from you. Also, you can join up my Facebook group, The Rational View. Love to have you. Love to chat with you. So here's the scenario. And we've all been there. You're challenged by a Young Earth Creationist. You're on the spot. They say, Bishop Ussher has traced the genealogies in the Bible back 6,000 years ago. God created the earth on a Thursday afternoon. What can you pull out of your head to refute that or to show the scientific evidence that is completely incompatible with this literal interpretation of an obviously allegorical book handed down orally from nomadic tribesmen? You'll tell them the science. You'll say, the science tells us that the universe is 13.8 billion years old. But then what will you say? What facts do you have? What information can you use to convince them or to convince the people that are listening to your discussion that you're correct? They'll say, nobody was there. It's just a guess. Scientific theories are just guesses. Nobody observed this. This isn't true science. What can you pull out of your head when you're on the spot about the age of the universe? Why is it more than 6,000 years old? How do you refute this book that this person has interpreted in their own literalistic, simple way? You're on the spot. What do you say? If all you've got is vague recollections of science class, you'll probably scratch your head and start ridiculing them. And that's not helpful. It doesn't help to educate anybody, and it makes you look lost. It makes you look like a fool. Now, maybe on the spot you're smart enough to realize that the size of the galaxy is 100,000 light years, and that means that there's stars that you can see with your unaided eye that are more than 6,000 light years away. So how could the universe have been created 6,000 years ago? the star Rho Cassiopeia is the most distant visible star, magnitude 4.7. So visual magnitude 4.7. That's reasonably seeable in a normal sky. Probably not in a light polluted city, but in a normal dark sky, you could see Rho Cassiopeia. This is a supergiant star, 8,200 light years away. So by looking at that star, and you can find it in a star chart, you can point it out to your creationist buddy and say, that star, the light that we're seeing from it originated 8,200 years ago. We're seeing it as it looked 2,200 years before you think the universe was created. Now that's a bit of a problem, right? What do the creationists say then? Some will claim that the light was created by God on its way to your eyes. These young Earth creationists believe in a deceiver God, a God that lays fake evidence of age, and you really can't argue against that, right? If they're going to just twist everything to match their last Tuesdayism sort of simple Bible stories, it's not worth hurting yourself over. And there's no way you can change their mind. If they want to believe in a deceiver God, they can. This is for the people that are maybe able to discuss rationally and just haven't really thought about it. Maybe their leaders have led them astray. You don't want to argue with the people that say that the book overrules the primary creation, which is the universe. It's the universe. The evidence in the universe is the primary creation. Most religious people will agree with you that if we understand the primary creation, then we're getting closer to God. And this is how the early scientists felt when they were investigating the age of the earth and the age of the universe. It's not some sort of twisted test of faith. Now, others who are slightly more adept may attempt to twist the physics to claim that the speed of light has changed significantly over the past 6,000 years. And this is how we bring this observation into line with our simple literalistic interpretation of an obviously allegorical book, despite a total lack of evidence. So, I'm going to give you some tools to debunk this stuff. One way you can debunk young Earth creationism is looking at Supernova 1987A, or Supernova Sheldon, as I like to call it. You know, the previous two visible supernovas, Supernova Tycho and Supernova Kepler. The naming convention of supernovas is named after the first person to discover them. And this was discovered by Ian Sheldon, a University of Toronto grad student who was at an observatory in Chile. Now, the Americans call it Supernova 1987A because they don't want to name a Canadian as the discoverer of this. I'm just kidding. That's just a little jab. This supernova was in the Large Magellanic Cloud, which is a neighbor of the Milky Way, at a distance of 168,000 light years. And that's a pretty well-established distance based on knowing the intrinsic properties of the stars in the LMC. We can measure that distance pretty accurately. But that's not all. This is a self-sufficient proof that the universe is at least 168,000 years old. Now, you're not going close to the real value, but it refutes anything that you can get from a biblical genealogy. So this supernova went off, and there was a cloud of debris surrounding the star. Astronomers were able to see the light echo of the supernova from this ring of debris surrounding the star days after the initial burst. It lit up as the explosion light hit it. And we can measure the angular size of this ring on the sky. And this particular geometry and the speed of light constrains the speed of light quite accurately over the past 168,000 years. If you think about it, if the speed of light were significantly faster in the past, then this ring must be much bigger than we think, which makes the supernova further away. So there's no way they can argue their way past it. It's a simple geometry thing. So that's one. That doesn't really tell us the age of the universe. That just refutes the young Earth creationists. So how do we know the age of the universe? Well, radioactive dating is one of the key scientific applications that tell us the age of elements in the solar system. It relies on the measured decay rates of long-lived radioactive nuclei. And by measuring the ratio of the daughter isotope concentration to the original isotope, you can estimate the age. But aha, says the devil's advocate. Don't you need to assume the initial concentration of parent and daughter elements for this ratio to work? Well, naively, yes. But in actual fact, no. There's a way to get around this, and it's called Isochron Dating. And if you have some time, please look it up on Wikipedia. There's a good entry. Isochron, Isochron. It basically normalizes both the parent and the daughter element concentrations by ratioing it with a stable daughter element that doesn't participate in the nuclear radioactive decay process. And this produces results that are independent of the initial concentrations, assuming that the rock you're dating remains chemically stable. Now, using radioactive dating, we've measured all sorts of rocks all over the Earth. And the oldest rocks on Earth are the Nouveau-Agatuk greenstone belt on the coast of Hudson's Bay in northern Quebec. And rocks in this formation have been dated to 4.28 billion years ago using ancient volcanic deposits called faux amphibolite. When I originally wrote this talk about 15 years ago, the oldest rocks known were 4.03 billion years old. In addition to these rocks, there's actually been zircon crystals in the Jack Hills of Australia, and these individual crystals have been dated to 4.375 billion years old. Other rocks in the solar system from other planetary bodies have also been dated using radioactive decay strings. Moon rocks, lunar anorthosite, have been dated to 4.46 billion years old. The Allen Hills meteorite found in Antarctica is actually a Martian rock, and it's been dated to 4.09 billion years old. So you can see we have a really interesting cluster of dates around 4.3, 4.4 billion years old. They're 4 plus anyways. And that's an important thing because this actually tells us that the age of the solar system is about 4.4 billion years old, 4.5 billion. So how do we do this with radioisotopes? I've talked about isochrons, and there's more than one radioactive pathway that you can use. You can use lead and its daughter element lead, lead-206, lead-207, and either lead-208 or lead-204. You can use uranium-plutonium, rubidium-strontium, lutetium-hafnium, rhenium-osmium, samarium-neodymium, and argon-argon. And all of these independent radioactive elements give consistent ages. And if they don't, there's something wrong with your rock. It's been melted or recrystallized sometime in its history, and it's going to give obviously weird, screwy results. And that's when you throw it out. If you're in science. If you're a creationist scientist, you will say that this disproves all of radioactive dating. But anyways, what I'm telling you is we have consistent means of radial isotope dating of rocks, and they're showing dates on the order of up to 4.5 billion years old for rocks in the solar system. But that just gives us our solar system's age, and that doesn't give us an age of the universe. So what other ways can we estimate the age of the universe? Well, you can look at the age of globular clusters in our galaxy and in nearby galaxies. And these are large clusters of stars that are self-gravitating, and they orbit around the Milky Way, and you can see them with your telescope if you get into amateur astronomy, and they're really cool to look at. There's very dense central clusters of stars. And when I took intro astronomy, first year university, one of our exercises was to take a bunch of observations from a globular cluster and plot them on what's called a Hertzsprung-Russell diagram, where you plot the magnitude of the star, the brightness, versus the color. What you find is that in any group of stars, they have a very characteristic line that they trace out in this diagram, and it's called the main sequence of stars. So when stars are burning nuclear energy, they have a very linear, log linear relationship between luminosity and color. And they work along this line, and then when they run out of their nuclear fuel, and the brighter, hotter ones run out of their nuclear fuel first, they leave the line, and they leave the main sequence and they go off in the asymptotic giant branch. They become red giants, effectively. And so wherever you see this diagram bend over, all the brighter stars above the color that it's bending at have already expended their supernova, their nuclear fuel from when they were born. And all the ones below it, the less massive stars, are still on the main sequence. And the position of that turnoff tells you the age of the cluster. If you assume all of the stars roughly formed from a cloud of primordial gas at the same time, and they're roughly the same distance, then you get a nice clean graph. And from the turnoff point and knowing the distance to this cluster, you can measure its age. And the oldest known globular clusters are 13.5 billion years, give or take a billion years or two. So wow, this is great. We've got something that tells us the age of a self-gravitating cluster of stars, and the oldest ones are 13.5 billion years old. Wow. And we can just tell this by looking at their brightness and their color. We also need to know their distance to do this. And the way we can do this is mainly through a special type of stars called RR Lyrae stars, which are pulsing stars, and their period of pulsing has been found to be directly proportional to their intrinsic brightness. So we've actually been able to measure some of these RR Lyrae stars and nearby to us, so that we can measure the parallax to these things, and so we can actually geometrically measure the distance to some of these stars, and that's how we found out that this relationship existed. So we use these things to measure distance to star clusters and nearby galaxies, if we can measure the period of these pulsating stars. So here, now we've measured globular clusters, and they're 13.5 billion years old. Are there more ways we can measure the age of the universe? Well, yes. We can also look at white dwarf stars to get an estimate of the age of these globular clusters. Now, what are white dwarf stars, you might ask? Well, I'm glad you asked that, Al. White dwarf stars are basically just stars that have used up their hydrogen fuel, but didn't go supernova. They weren't big enough to go supernova. They've had a planetary nebula stage. They've gone supergiant. They've pushed off their outer envelope, and now they're just kind of a hot stellar core of gas. And they're just cooling under their gravitational pull. They're collapsing and cooling, and they start out white hot, and they cool over time. They no longer have enough mass to do nuclear fusion in their cores, so they're not burning chemical or nuclear energy anymore. They're just fading embers glowing from residual heat. And the oldest white dwarfs will be the coldest and thus the faintest. And the Hubble Space Telescope has gone off and to say the M4 globular cluster and search for these faint white dwarfs. And using models of stellar evolution, they can estimate the length of time the oldest white dwarfs have been cooling from their temperature, their color. Temperature and color are very synonymous in optical physics. And based on physics of thermal emission and chemical composition, and assuming carbon-oxygen cores and a few different aspects of stellar evolution, chemical layering due to gravitational sedimentation, lots of big words. Using our models, we can basically measure the age of these clusters. And M4 is another cluster of stars, 5,600 light years away in the constellation of Scorpius, if you want to go look at it with your telescope. And the Hubble Space Telescope made some observations back in around the turn of the century, over a 67-day period, down to 30th magnitude, looking for the dimmest bright white dwarfs. And what they found was that based on the dimmest white dwarfs, the M4 globular cluster is about 12.7 plus or minus 0.7 billion years old. So here's another somewhat consistent measurement. We're getting numbers of 13.5, 12.7 billion years for these globular clusters. What else do we know? Well, astronomers have also found what they think is the oldest star known in the galaxy. It's got a very prosaic name called HD 140283. They call it Methuselah's star. It's 190 light years away in the constellation of Libra, and based on its chemical properties, its color, its temperature, all these things, we can look at a single star and try to predict its age or guess its age. And based on the models, This star is about 14.3 plus or minus 0.8 billion years old. Now, interestingly, this comes out actually older than the age of the universe as far as we know it, which is 13.8 billion years old is the accepted number. But there's still a lot of uncertainty in that, and hundreds of millions of years, depending on the model that you use to estimate the age. So it's consistent. It's a little bit worryingly old based on the numbers, but it's not orders of magnitude out. It's not giving us inconsistent numbers that would cause us to question our models. Okay? At most, this is a tweaking of dials and details to bring these things into alignment. So what are other methods of measuring the age of the universe? Well, you're probably familiar with the cosmic microwave background, and this is something that astronomers love to look at. It's the echo of the Big Bang, the radiation left over from the Big Bang, echoing through the universe for billions of years. And it's a perfect black body spectrum. 2.7 Kelvin is the estimated temperature that it looks like to us now as the light has been stretched out by the expansion of the universe over the last 13.8 billion years. And so this is really cool. We can look at the Big Bang explosion in all directions, and it's around the same temperature, and astronomers have their cosmological models that they can apply. And the most well-supported cosmological model gives an age of about 13.7 billion years, using microwave background observations and measuring the fluctuations in this microwave background and the models of cosmology and general relativity equations. They can use this data to constrain the age of the universe. So, again, this is amazing that it's consistent with the ages of the globular clusters. It's consistent with the dynamical age of the universe. We can look at different markers throughout the history of the universe, looking back in time, looking farther off in the distance. You can look at supernovae over the history of the universe and measure their brightness versus their distance. And their distance is calculated based on their redshift. Redshift is how the light from the supernova has been stretched as it goes through the universe due to the expansion of space-time continuum. So we can actually plot points all the way back using these type 2 supernovae and calculate what they call the Hubble Constant. This is the reason the Hubble Space Telescope was named the Hubble Space Telescope, was it was going to measure the Hubble Constant. And the Hubble Constant is the accelerating expansion of the universe as you go further away. It's basically accepted as something like 67 kilometers per second per megaparsec. And a megaparsec is like 3 million light years. And using the type 2 supernovae observations, which earned a Nobel Prize for identifying the accelerating expansion of the universe over time, the age of the universe is 13.8 billion years. So we've got several independent methods that I've given you. They all give roughly consistent estimates of the age of the universe. I mean, these are all younger than the age of the universe, but they're all very consistent. And this gives scientists confidence that when they say the universe is 13.8 billion years old, they know what they're talking about. And what does this mean for how big the observable universe is? Naively, one might assume that the observable universe has a radius of 13.8 billion light years, right? Because light travels at the speed of light, and we know it's 13.8 billion years ago old. But that's not the real distance, because the space that's been traversed by the light from the cosmic microwave background, which is the furthest thing we can see, has been stretched due to the cosmic expansion since it was emitted. So the regions of the universe represented by that background radiation have been expanding away from us after they emitted the light. And the expansion of the space-time continuum is actually means these things have moved away from us at faster than the speed of light at the edges of our universe. And what they call the co-moving speed, assuming regions of equal age at rest versus the Hubble flow, the galaxy supergroups that represent the ripples that we can see in the cosmic microwave background are now at a distance of something like 46.5 billion light years away from us in both directions. If you integrate the accelerated expansion of the universe as we now expect it, as we now think it happens, So the universe itself is like over 90 billion years in diameter, the universe that we can see. And it's filled with galaxies, and it's filled with stars. And it's amazing. And I always get burnt up when you hear these people saying, but in science you have no real sense of wonder because you understand things. No. Science gives us so much of a grander sense of wonder, knowing the awesome grandness of this huge expanding universe with billions of galaxies, each with hundreds of billions of stars. It really puts you in your place, doesn't it? I hope you enjoyed this. I really loved talking to you about it, and stay tuned for next week. Thanks for listening to The Rational View.
If you're enjoying what you're hearing, please consider visiting my Patreon page and becoming a patron of this podcast at patron.podbean.com/TheRationalView.